Okay, Rich Russel. I'm just out of as the president of the Deep Space Exploration Society. We are a radio astronomy group in Colorado. We have a 60-foot dish on 11 acres of land, an old tropospheric dish that they've been upgrading for the past 10 years, 11 years. And they've just got it working. We've got a hydrogen feed on there. And we've been taking measurements. We've been collaborating with Skip Curley. You'll get his presentation this afternoon on doing dual measurements, simultaneous measurements with a 40-foot dish out here. So we got a lot of good stuff done. We are basically like SARA. We are a group of people that are just going there and getting a 60-foot dish, which when we originally got it, all the copper was removed, the motors weren't working, and they basically returned this thing to life, and it's now working pretty well. My background is I'm a retired Navy submariner who shifted to building Navy spacecraft, who then shifted in my contractor years to building big ground stations. So I used to be the chief architect of the Air Force Satellite Control Network, which has 13 dishes all around the Earth. And then I retired from that, and I figured out what can I do for fun? Radio astronomy, and radio astronomy is kicking my butt. All right. So my goal was to originally start with the SuperSIDs, a Radio Joe, all the basics, and trust me, that's getting me to the point where I actually think I know what I don't know. So it doesn't mean I know anything else. And I'm very much like the last speaker. My job at the Deep Space Exploration Society with all these technician guys who know how to build things is to build a lousy prototype that sort of works. They get mad at me and they fix it. And I get up with this, we get up with this great thing, but I do it because they don't think, they just hate the way I build things. My Radio Joe had I followed it exactly using plastic rods, and it was bending and all that, and now these guys put up big steel poles, right? Because they hated the way I did it. So my sort of goal is to be an amateur astrophysicist, by the way. Last year, you guys, when I presented this, I went, hey, the eclipse is coming up. I think that with a SuperSID, you're going to see a bump. Here's my analysis of that, and to be an amateur astrophysicist, you have to predict something. So I did it right at this meeting, right before the eclipse, and now I'm ready to present my results. It's in the journal, the month after I published the results in the journal, and it worked. So I'm an official amateur astrophysicist. I predicted something and actually came to So I'm following up. This year I'm following up. I'm going to predict something else, and it's in galaxy stuff. So I'm glad you were right in front of me, because I'm doing galaxy astrophysicist. And I'd like the check from the NSF after the brief. Okay, so what did we get from the eclipse, August 21st? This is my SuperSID's output. Now the nice thing here is that I don't show the plot. In Colorado Springs, the actual transmitter is almost exactly halfway between where the eclipse was going to do the pass. And so I've had this thing, I've been taking data for 2 years, and now all of a sudden I get this eclipse that's going to pass halfway between me and the thing. So I came up and I said, hey, all an eclipse is nighttime, this is what happens at night. It goes up very fast, and in day it goes down very fast. So I said, hey, well, based on this, and when the time of the eclipse is going to happen, here's the rate that's going to go up, and here's the rate that's going to go down. So I actually predicted that it's going to look something like this. And this is the actual plot that I actually got. And to show you how close I was, this is the actual, and this is what my predicted was. And then this is, I mean, this, you can't even tell on this chart here, it'd be just barely thing. So it worked. The data analysis I did worked. That it's actually, an eclipse looks very much like a day to nighttime transition. It's just shorter. Okay? And there's a couple of little variations. You get really down to it, the slopes aren't quite exact, so that's some follow on. The other thing we discovered was that I have a big mountain called Pikes Peak to my west, that I actually get different slopes. That slope is different because I have Pikes Peak there. Guys in Arizona get more of a steep up and then steep down because they have no mountains. So somehow the mountains affecting my rise and fall and my SuperSID data, you know, affecting the ionosphere. So I wouldn't have gotten that with the eclipse because the eclipse didn't have it. So anyway, so we got that. Just for things, I am in the AFSO. There is an AFSO SuperSID observing team who's been observing for 10 years. I've been entering my AFSO, my SuperSID observations for the past 2 years, and these are the other observers that are in there, and basically they all saw the same thing. You know, this messy guy here, but fundamentally they all saw the thing. And one of these guys is down in Mexico, etc. Finding some research, guys who have long baselines like in Antarctica, there's actually some guys had a negative drop. So there's some kind of a phase variation there. And just to throw there is new science here. All these guys had this dip right here, which is pretty much just after the eclipse. Everybody had a drop. And I have no idea what that is. But just notice every observer had that. So there's something going on after an eclipse that will cause a steep drop and then it returns. So I throw that out to as an amateur astrophysicist that there's new science here that I have no idea why it's doing it. We've got a lot of observers that saw it. Okay, also on SuperSIDs.
Rich, what was the time delta between the end of the eclipse and the anomaly?
Let's see. Let's say 1800's the center of the eclipse. 912 is the 1912 is the anomaly. So here is the. So you see the slope there. So right about here was the end of the eclipse. So it's really close to the limb, the end of the limb. So it's almost the exact end of the eclipse. So there's something that caused a drop in all the SuperSID's data, that same drop. And it happened to everybody. So I thought it was just mine. Didn't know why, but maybe it's some kind of a flash, or saw something that just as that limb exited. I don't know. But it's an interesting phenomenon. Next, in 6 years, we have another eclipse. I'd love to sit there and have people look at that and zoom in. Anyway, by the way, I do highly recommend this in 6 years for the new eclipse. I mean, we should be able to see it in North America. But theoretically, you guys should be able to see eclipses even though they aren't passing through you. You might be able to see an eclipse. You just have to find a transmitter that's passing through an eclipse even though it's not North America. So think about that if there's other eclipses around the Earth, and there always are, that if we can sit there and find the right transmitter or receiver combinations, we can go do this around, not have to wait for the North American eclipses. Okay, questions on the eclipse. Basically, I told you guys I was either going to not ever bring this up again, or I was going to be a folklore hero last year. So I'm deeming I'm an amateur astrophysicist, and I'm folklore because I predicted this, and it worked. Okay. Now it's interesting that since I send these charts in all the time. By the way, this is called SID Grabber. You can download it on the AFSO website, and what it does, it pulls up all of the data from the National Weather Service and plots where the flares are and what the levels are. So this isn't me telling you what that is. It's basically, if you're online, this SID Grabber will pull your data from your SuperSIDs, and then it'll overlay what the actual measurements are that the satellites are giving you from GOES. And so on this day, we started to see some X and M flares. Now, an X flare is the highest flare level, and theoretically 1.9 is the highest flare. I'm sorry, 9.0. They go in 0 to 9. 9.0 is the X 9.0 is the highest flare that they've got a record for. all right? And M's, so it goes X, M, C's, B's. Okay, so when you start getting, so normally you get C's and B's, which are down here, you see the little bump you get there. M's are second highest levels. X's are your highest levels. So here, September 7th, I saw an X 1.3 flare, and that gives you a huge thing. And basically the way the flare works is, flare happens, it ionizes the atmosphere, causes a reflection from the submarine transmitter, and you get this big burst up here, and then basically it recovers and it gives you this nice shark tail, or shark fin approach, okay? So that is what you're looking, if you do SuperSIDs, that's the classic what you're looking for. You're looking for that shark fin. All right, and that gave you, and then if you use SID grabber, you know exactly that yes, they did have one there, and so you can sort of correlate it, because sometimes you get trash here and you're not sure if you really got one or not, but this sort of tells you, yeah, you actually had one. So next 1.3. Boom, September 10th, an X 8.5. This is what happens when it takes out the entire ionosphere for the entire day. All right? And so this is, if anybody has SuperSIDs and hasn't recorded, go look at September 10th, right here at 8.5. Remember, it only goes to 9 in the scale.
Well, it does go higher, but there's no letter.
There's no letter, right? Yeah, yeah, but so you got an 8.5 here. So anybody who did SuperSIDs, this is why I like SuperSIDs. One, the software is easy. I've got it. It's a little snuff can receiver. I've got my little wire thing, and I've gotten great grief about from all my guys because I built it, and I'm a lousy builder, but I put a lot of wire in a box, but I've left it out for 3 years, and I get good data. Okay. So anyway, look at that. So you got an X 8.5, and I also documented all this in the journal.
Now, how is that flare different from a lot of others? Because I had a system going at 408 megahertz, and it basically pinned out the receiver that day. Most flares don't even show at 408 megahertz.
Well,
I mean, you know, it pinned out right at the time that the SuperSID people were saying, yep, it's there.
okay,
And it pinned it.
okay.
It was strong.
Well, okay, yeah. So the way SuperSIDs works is, we got a submarine transmitter about at 25 kilohertz, so it's very low frequency, right? And then the ionosphere basically goes up and down with day and night variations. As soon as you get a flare, it ionizes it, and it causes a reflection to happen.
Right.
And so you get this great big signal jump. And by the way, it should be, this is why at night you got the highest power here at level at night, but in the daytime it drops it down to nothing. Well, this basically makes it look like a nighttime. And then it recovers and it gives this nice start. This is the, I think I've never heard anybody else get a nice, pretty signal on SuperSIDs like that. But if you've been recording, look for this date and see if you've got it. And I think it's only because you're doing bistatics with SuperSIDs.
See, I was doing 408 megahertz, so I was getting direct radiation.
You're direct.
I was getting direct radiation from the sun. And most of the time, I watched the radio astronomy group and see people always saw a flare, and I take a look at my results every couple days before the data recorder overflows. And since September 10th, I've not seen another thing. I saw one thing that might have been a slight effect, but that one, it blew
it away, right?
It was strong.
I've been, this last 6 months, there's been hardly any activity. My thing's been dead for the last 6 months. And I keep thinking it's my wife put clothes on it or something. It still looks good. Still where it is. Yeah, but I think it's just the sun. The sun's very non-active right now. Which ought to make the ham radio operators really upset. Yeah.
So when the flare happens on the sun, when do you see it on the receiver?
I don't
Is it
know.
11 minutes later?
8 minutes at least, and then
That's when you see it.
It's caused by the X-ray, so it's 8 minutes.
so
The ionization happens pretty quickly.
Yeah.
It's just that the
But
case
it's
will
not 2
accommodate.
days later?
No.
Oh no, it's almost the same.
CME type stuff.
It's almost immediately.
Yeah.
It ionizes, it just slams the ionosphere, and then this VLF signal from the submarine transmitters that's really what you're seeing. It's got a beautiful reflection path.
Sure.
And if you saw it, just like you saw my eclipse one, if you had, if you were at different locations, you would have a different amplitude based on, you know, almost what's your max nighttime conditions. You know, but when it really slams it really makes it reflect, and now you get this, you get almost all the signal from that, and then you get it beautiful. And then you see, the nice thing is it's recovering here, so it basically becomes non-reflective. It gives you this nice, pretty exponential decay curve.
So it enhances the reflections,
Right?
right? Whereas in ham radio, I'm a contester, and some weekend I'm contesting along and making contacts all over the United States, and all of a sudden, it shuts off when a flare occurs. So what's happening?
Depends on what you're bouncing the HF, you're doing HF, what's it bouncing off of, and what happened to that layer?
Yeah.
So
This
you're going off that layer, D-layer became ionized and absorbed.
I kind of thought how this worked, and people are going to tell me, since it's been years since I've been here, but I remember when they got started with SuperSID and they built all this stuff back in the day. I thought that you were listening to the VLF beacons, essentially the submarine transmitters,
Right.
and you were observing them at a certain level. And then when you had a solar flare, it ionized the ionosphere greater, so that you had greater depth of ionosphere. That moves the plasma down closer to the surface of the Earth,
Right.
and then you got less signal.
You get more signal. You get more signal when you get a flare.
Okay, tell me, Tom.
Over here.
Yeah.
I believe, I don't know this for a fact, but I believe what happens is the D layer is ionized.
Okay.
And these frequencies are such long wavelength that I think the plasma frequency of the D layer allows the
So it's the D layer that's now reflecting as opposed to the E layer which gets slammed
It's the
down.
VLF that it absorbs the higher frequencies.
Yeah, that's it.
So what are you saying, Tom? You're saying it does get more reflective when or it gets less, or you get less signal?
You get more reflection, and because it's the D layer, it absorbs the higher frequency, but it actually enhances.
See, but the whole idea of the submarine signaling system is that propagated around the entire Earth. That's what its use was for. And so you were able to get a signal anywhere all the time, basically.
So I think normally we're receiving ground wave.
Right.
Okay.
Yeah, the reason you have,
That would make a difference.
being a submarine ex-navigator, and I'm going to go into that in the next talk, the reason is because it can penetrate the ocean.
Yeah,
I
it's
don't
not
have
about
to come up to
100
the
meters.
surface to get comms, even though I have to, it's 1 bit per 100,
Just tells you to come up to satellite.
says, yeah. And my wife she only had 30 characters to send me a note once a month. And that took 20 minutes to get her 30 character thing in, and so she lets me know about that. So, it's like Twitter, slow Twitter.
I believe it's 50 baud.
And it was really low. Then as an officer, you had to sit there and review these things because wives were divorcing guys, and they had 30 letters to tell them that they're divorced, and you had to sit there and say,
Man, that's a short Dear John, isn't it?
he's not going to see that one. All right, yes, sir.
Back on the last graph, how do you know what frequency you're looking at?
This is, because you picked NML. NML is was the transmitting station. NML is at a certain frequency.
Okay, fine,
Yeah.
but how do you know your radio's picking that one up? I'm
Okay.
throwing the thing
It's
back.
FFT-based radio, right?
SuperSID records based on the frequency, and if you see the spectrum plot, it has the different spectrums, and it records that, so it picks the NML frequency and gives you the NML one.
That's that special software.
The software, right.
Okay,
And
so
so it also
or whatever you call it.
It also records a different frequency for the other transmitters around. So you can actually, depending on which one you pick, you have a different geometry.
Sure.
But if you use the off-the-shelf software, it shows them all.
If you use the off-the-shelf software, you can pick the different stations too.
Okay.
It just doesn't give you it doesn't give you this. It doesn't give you the data from the GOES. And I just, in fact, the AFSO guys want you to use this because what I can do is I can sit there and I can click this point, that point, that point, and it'll actually put it in a report, and the AFSO guys take all the reports and they can automatically absorb it and then analyze it. So this is, they basically made a tool that they can convert that into digital and then report on multiple observers.
Is this a talk on SuperSID or?
It's not, this is an update.
Because I have an antenna question.
Sure.
I want to build a loop in the attic of my house that goes around so it'll be horizontal rather than vertical. What's the upside, what's the downside to that? Because it'll be about, probably, a 400-foot loop.
It's, all the ones have been vertical, so the question is, do you got vertical and horizontal, you're gonna lose gain?
I believe the electric field is vertical.
Yeah,
You're
not gonna couple to the field properly by doing that. That's the problem.
Yeah, vertical and horizontal, I mean, that's almost 100% gain loss. So I believe these are all vertical transmitters. At least all the SuperSIDs have been vertical, so I don't know about 100%, but that's
Probably not a good idea.
yeah, I would say just go ahead and put a small one with a lot of loops on it, vertical in your attic, and you probably get better gain. Okay, I was trying, as your new amateur astrophysicist, I've been, my goal was, and we've been doing hydrogen, and was, hey, and as a navigator, an ex-navigator on a submarine, which I believe submariners should be the new astronauts because we've got a nuclear power plant behind us, we're in a tube with a lot of guys, smelly guys, and we got things outside us that are bad, right? So the perfect, and we go out long periods of time, and it's just, we're the perfect astronauts, right? And I have nothing, I can't even look out the windows, right, except this little periscope, right? We're the perfect astronauts, everything's by sensors, right? So I had to go navigate across the Pacific, I'm a Hawaii sailor, navigate across the Pacific without ever seeing where I'm going. And then get back, and then surface and realize that I'm at home port again, right? So we did that all the time. So that's exactly, so I sit there and say, how can I use that theme in my new astrophysics career, amateur astrophysics career with you guys? So we do hydrogen, and we do velocity measurements and Doppler shifts. So I'm very interested in the rotation rate stuff, okay? So what I want to show here is that if we take hydrogen and measure the rotation rates, your classic is how fast, your Earth's going around the galaxy, and you're measuring hydrogen at a certain galactic latitude or longitude, and you're seeing a velocity jump, right, based on how fast the relative speed is between the two objects. So I wanted to go turn this hydrogen measurement into a navigation aid for galactic, travel. And what was my theme there? We've got somebody from, we're actually doing this at DSES and SCIP, who's got, we're looking at 40 Eridani, SETI. So if a spacecraft's coming from 40 Eridani and coming toward us, what galactic sources would he use? What would he see from hydrogen in order to use as a galactic aid? All right, so that's my whole thing, right? As a navigator, I want to, if I'm coming from another planet in the galaxy, what would I see? And none of the math currently is worked out for not being on Earth, right? So this math will convert it so that you could be anywhere in the galaxy, and you can convert your Doppler measurements for any of these galactic sources from wherever you're on Earth and use it in transit. Now, I don't go into how you got there, right? And you didn't use warp speed to get there. You just happen to be plopped somewhere between Earth and Keed, which, by the way, is Vulcan for you, right? You're plopped somewhere in between there. You got there somehow, what would your hydrogen measurement be to tell you that you're actually there, or you're on course or off course? That's the goal of this paper. Okay, what's the math? Because nobody's done that because nobody cared that they were here, they always cared that they were always on Earth. Okay, so that's the goal. So first you get the rotation rate formula, so we're going to go over basically all that. Then what's your geometry for galactic travel path? So we also have to account that heat is actually below the galactic plane. So we're going to travel from the sun to the Keyd, and we're going to use that Doppler data to figure out where you are in the galaxy, where your spacecraft is in the galaxy. Okay? And then I'm going to say, based on that, I can actually figure out, are you guys sailors or pilots? Right? So when the wind's blowing, you're pointed this way, and the wind's going this way, you're pointed that way to go straight, right? Well, the Navy does the same thing, right? So now a spacecraft is all this your galactic rotation actually like a current moving you, right? Because you're going 220 kilometers per second is the rotation rate. Well, if you go past outside that gravity, you got all that pushing you, and are you actually being pulled with it, or are you actually being left in the dust because you have no current? And meanwhile, everything else is keeping moving off. So that's, I'm trying to answer all that. So we've got course velocity, galactic current indicator. So I can actually determine, based on this, how fast my spacecraft is going based on the galactic center. And what my velocity is, if I'm off course or on course. And then I got issues to be solved. There's a couple, like, how did I get there and stuff. And then I got a couple future projects. Okay, and went over this. There's actually 4 quadrants. Here's the sun. Here's the galactic center. But our current galactic thing is based on the sun being the center of the universe. All right, we're going back to, Aristotle and all those guys, Ptolemy, and galaxy stuff. We want to be modern, so we're going to have to shift this to the galaxy is actually the center of the universe, not the Earth, right? So I don't know what the galaxy guys were thinking of that they thought that they could go back. But anyway, so right now, the sun is 0, 0, and then here's your galactic coordinates, and then this is the galactic center here, and from a latitude point of view, you basically got up and down the galactic planes here. So Keyd's actually down a little bit in the galactic plane. And that's important because this thing's rotating like this, or like this, and the lower level planes are not rotating at the same speed. And Keyd, which is Vulcan, is in a different rotation rate than the Earth is. So I was going to fly there. I've got to go fly into a different rotation rate, and do I actually get pulled? What's keeping me in that same rotation rate? All right, now realize both of my pitches have a lot of math in them, and they put me right before lunch and then right before dinner. I'll tell you, so if I see people nodding off because of lack of sugar, it's okay. Okay, I teach master's degree students, so I'm very good at doing that. Okay, so a little math. And a thing, if you're going to do galactic rotation rates, and here's the sun, and if you were between the galaxy center and the sun, is a different formula than if you were out here. Right? So out here you can have stuff, but it's a slightly different formula. Right? And so the velocity you measure on your hydrogen measurement here is a combination of the velocity the sun is making toward that object. Say this is the object you're measuring hydrogen in. It's the combination of that, you going in that direction, and this coming in that direction or away from you. And that's your combined velocity or Doppler shift. So it's all about Doppler shift, okay? So that's your VR. Now this here is your contribution of your hydrogen interstellar mediums, basically ISM. That's your contribution of that going away or toward you, and this is the contribution of the sun going around the galactic center toward you, right? So that's VO. VO is your or about 220 kilometers per second around, around the galactic plane there. So anyway, this is the distance, and this is galactic latitude. All right. So that's the basic formula. There's also another formula for if you're outside the galactic plane. And by the way, T is right here. So I had to go get this formula. And I need to write these. These are well-documented formulas. But I had to go convert all this thing to the galactic center because nobody cares at T that you're using the 0, from the sun, because they wouldn't use it because that's not their galactic center. So I had to convert everything to galactic center coordinates, which is part of the math here. There's a couple databases that have historic hydrogen measurements. And so what you had to do is basically I kept latitude 0, which means I'm on the galactic plane, and I just had to put the galactic longitude, and then it gave you a velocity curve for that point from the history. Now it's interesting that the maximum velocity tends to be the source that is almost tangent, the closest, that maximum velocity, the guy closest to the galactic center, because it gives you this and it's moving the fastest compared. So realize that it's called the tangent method, that the distance to the galactic center is, closest to that is the highest velocity you get on your Doppler shift. All these other guys, here, here, and here, are either closer or either here, because it's all along the same line. So either here or they're here. All right? The highest velocity is the guy closest to direct tangent here. So I just realized that that's a theme of the stuff. Okay. Now, if you measure all this stuff, and this is still coming from this database, you'll find that the rotation curve, so how fast is the sun going around, or how fast is the galaxy moving at the sun's location, and you'll find that it gives you a nice curve here, okay? Now there's other things here, that there's other little subcurves that build up to that, but basically this gives you this database. So one of the key things is that one, you don't know the locations of these points exactly in an XY coordinate scheme. You just know that they are so distant from the Earth. So what I had to do is convert these to an XY, what's galaxy now the center, what's an XY coordinate system in the galaxy? And then plot all of these points. So, I throw this stuff in because there are a couple geeks here that come to me and say, show me all your math and your paper. So I do. So realize this is for the geeks who are going to come to me and say, you missed something, right? I'm perfectly happy to put my math here. So I'm waiting for someone to do that. Somebody saved my bacon last year because they told me that I was off by 0.2 or something. I said, oh, let me fix that. All right, so what I do is I took the data, I plotted it, and I came up with a formula. It says, based on the distance from the galactic center from all these hydrogen points, what would the velocity be in kilometers per second? This is just the data points plotted out, but then I came up with a formula for it because I had to go reproduce it. It's not a great fit because a lot of the stuff, when you get down below here, it's not really following a flat curve. But everybody hears about the dark matter that's causing the galaxy to move in one, like a frisbee. It's all moving together. Otherwise, it would look like a swirl, like you're flushing your toilet, it's a swirl. All right, that's the dark matter part. It's flat past here, but interior, it's not as flat. So it doesn't fit very well here, but when you start sitting here, you start seeing it's pretty flat. All right, which means that between like 4 and 8, by the way, we're at 8.5, we can pretty much predict what our rotation curve is. We're all moving together like in a record, right? At galactic plane of 0, not below or above, right? So if you do that, what I wanted to do is take all these galactic points here and come up with an X, Y, Z plot of where they are based on the galaxy being the center of the universe, not the sun. Okay, so now I can do a plot. So here's a 0, 0. So I'm looking at these, galactic over here. these are where the galactic points are, based on an XY plot of, Cartesian plot of the galaxy. Just looking, you know, and here's where the galaxy is, and then here's, basically, we're right here, 0 here at 8.5. That's where the sun is, and this is where all the other points are that I found. So this is very useful from a galactic navigator point of view, because I don't know what the sun's, I don't know about our sun's galactic coordinate system, but I know I should be able to figure out where the center of the galaxy is and make a common coordinate system for the Vulcans and us. This, I threw in there spherical, I had to go use spherical coordinates to come up with some angles, but fundamentally, and this is where I'm geeking out here, this is the galactic center, this is us, and that is key. What's the map that says, hey, how can I figure out where I'm at, the distance I'm at, and what's my Doppler shift here, and what would I see here on Earth, and what would I see here? So this math basically will tell you, based on the galactic center, what the math for the Doppler shift would be. This is actually the change in velocity. This actually gives it to you here. So that means that anywhere in the galaxy, I can calculate the Doppler shift, where that point would be based on any point, any hydrogen source in the galaxy. That make sense? So all these hydrogen sources are moving around the galactic plane. This point's moving around the galactic plane, but it's not the sun. What is it seeing the Doppler from that point is? So now I can use that as a galactic navigation aid. That makes sense? Anybody really? I was hoping I'd get a couple.
Isn't there enough symmetry there that there'd be 2 or 3 points?
Yes.
That make the same mathematical.
Absolutely. So you have to actually take. You will get hydrogen. You'll get the same Doppler from a number of different points. So you have to take a number of different points to get the ambiguity figures. Okay. Yeah, there's a lot of ambiguity issues. So you at least have to take 2 points. And I'll show you how that works. Okay, so where's keyed? And it's Omicron 2, right? It's up here at Eridanus. This is Eridanus, right? And this is where Skip's been concentrating our SETI stuff on, is Eridanus. So you heard all about that. And that's why I chose it, because I wanted to go fly the mission that all the SETI guys were assuming was happening, right? So now I'm flying it. I want to say, hey, what are we seeing? So it's called either Omicron 2, Homestar of Vulcan in Star Trek, Homestar of Riches in Dune. Okay, so it has some mythology behind it too. Okay? So it's just not some star out there we chose. Okay, so where is it in the galactic? So if the sun's here, keyed is right about there. So it's a little north, there's a little, from 180, not north, but here's the galactic center, there's away from the galactic center, and it's a little off here, and then from an XZ point of view, it's down, right? So it's below us, and it's up a little north, okay? If you go zoom in, so this is now in galactic coordinates, XY, and this, by the way, kiloparsecs, okay? 1,000 parsecs, and parsecs about 3 light years. Okay, but these are, so if you think about that from a galactic center point of view, this we're at 8.5, and keyed is, it's over here, and then from an XZ point of view, it's down this many parsecs, 0.0035, 1 parsecs, in the X component on this side. Okay, so why did I do that? Because I needed to go figure out, I took that data from the last one and figured, well, where are my hydrogen points? So just like you're doing VLR flying in aircraft, right? You had to go figure out your points and then figure out what the bearing is to them. In the Navy, I'm using, I was a Navy navigator for that GPS. I mean, a real navigator. And these guys put your periscopes up, they get 2 seconds, they got a GPS coordinate, and they dive again. So what fun is that? So I had to go figure out where everything was, use Omega, Moran, all that kind of stuff. So that's my theory. Yeah.
5 minutes.
Oh, okay, so if you have a course, your sun and you're going to key, 25-50% of the travel distance. Okay, I made an Excel plot that basically took all this math, and I said, hey, if I take this, what would be, here's the XY coordinates of everything, of the position I'm at, where I think I'm at, and here's the source data, and then here's the frequency and velocity shift that would happen. So I took all that. I did it for two sources for ambiguity, and I'll tell you why I need that. So you take that and you say, hey, if I'm at this point here, my velocity here for that source would be this, and for the second source, I'd be this. So now I've got two frequencies that I can look at, and if they're at the same point, I'm at that point in the sky. So here's your source 1, source 2, you're traveling, and so now if you get a frequency here that says I'm only at 25%, and here it says I'm 35%, if I'm still seeing them both at the same time, I would end up at a point there, which means I'm off course. Right? Because I'm seeing two things, and one says that I'm at 35% of my travel path, one says I'm at 25%, but it's still both seeing at the same time, so that means I'm up here where they two cross. So now I've got an ability to come up with where I'm at and to tell that I'm off course. All right, and then what do? I simply do a course correction. And then I keep taking those data. And then you can automate this stuff and have it automatically tell you that you're off course, and you can put an autopilot in if you want. Okay, so velocity indicators. If I have a source here and I'm going this speed, hydrogen is really a Doppler velocity correction. So I can tell exactly that I'm going, if I'm just sitting there, I should see 100 kilometers per second. If I'm at 200 kilometers per second, I should measure 300 kilometers per second, because this is giving me, that's providing a 100 kilometer per second thing there. So fundamentally, I can tell my speed if I know that number. Right? If I'm off course, then I should be able to calculate what I should be, but if I'm measuring something else, I can tell I'm off course. And then I can tell exactly what the components be. So this is, for the real geeks, I can fundamentally tell that I'm off course based on velocity differences and what my speed is in the sky. Okay? And I'm going to go over this. This is what my position was. That this is a great high school project. That where's the Earth based on hydrogen, your hydrogen measurements. So all these hydrogen measurements you're doing, where's the Earth in its orbit? You can track that all along the year using the method I'm going to show in my next brief, right before dinner, right before when you guys don't want to see math either. Right? So I am. So what do we got to do? A lot of stuff. One is you want to map the sky better into galactic coordinates, galactic centric coordinates, not heliogalactic coordinates. Everything's about heliogalactic, which means everything's about us. Just like we went back in time in astronomy, back in the dark ages where we were the center of the universe. We did that again with galaxies, all right? So now we got to get back to the galaxies the center, and we have to have a galactic coordinates. Otherwise, we can't fly through the galaxy, all right? So I know why they did that, but you got to think ahead. Also going to do carbon monoxide measurements. That also give you a Doppler shift at just a different frequency. That can help some of your ambiguity issues. And we want to start taking data, see if this actually works. Okay, questions? Thanks. Oh, I'm sorry. By the way, this is our dish. The guys on here jumped onto our land and took this thing by trespassing. So we caught them. They're great photographers. So this is the galactic plane. This is during the meteor shower. And there's our dish. And that's, in Colorado Springs, right there. And so that's a meteor. That's the galactic plane. And so we made him a member of the club, and we said we got rights to use all their pictures, right? And they love us, right? So that's how you do it.